How about separation based on charge? I can do that too. And the technique I'm going to use to separate based on charge is called ion exchange chromatography. Ion exchange chromatography. Now remember, okay, separates based on charge. Now you'll remember that proteins, the amino acid side chains, right, some of them are negatively charged and some of them are positively charged, right? We all agreed that the amino acid side chains were a mixture of positive and negative charges, as well as all the others that we went through. And the ones that are negatively charged are what? Aspartate and glutamate. And the ones that are positively charged are going to be arginine, lysine, and histidine. And different proteins will have different amounts of these. And so at pH 7, or 7.0, or 7.4, some proteins are going to be positively charged, and some proteins are going to be negatively charged, depending on the relative amounts of arginine and lysine and histidine and aspartate and glutamate that they have. And so at a particular pH, if the proteins are differently charged, I can separate them on the basis of charge. And the trick here is to use a column of cellulose or agarose that contains charged groups. I'm going to start using the letter C with a line above it as the word with. It'll save us a step, okay? With charged groups. And the two best examples of this are what are called an anion exchange resin. Now, you guys probably know this, but let's just remind ourselves. An anion exchange resin exchanges what? An anion exchange resin exchanges what? Alice, what is it going to exchange? Yeah, anions, of course. So if it's going to exchange anions, right, remember, what charge does the column have to be? Positive. So it has to be a positively charged resin. And the resin that we typically use, an example of one of these, is called DEAE. And that's diethyl aminoethane. Okay, and it's basically a bead. Here's my bead. And off of it are many, many charged groups. I'm only drawing one of them. It looks like this. N, H, okay. So, diethyl aminoethane, DEAE. Anybody here ever seen a mono Q column? Right, or a Q column? That's what this is. That's basically this. Okay? Now, and this would work if my protein had what charge? Negative charge. This will work for proteins that have a negative charge. I can separate them. Now, what about cation exchange? Resins. So, if I have a cation exchange resin, Santiago, what's a cation exchange resin going to exchange? Cations, of course. And so what charge does this have to be? Negative, right? Because cats are positive, so cations are positive. So I need a negatively charged resin. And the classic negative charge resin that people used for many, many years is called carboxymethyl. Carboxymethyl, like carboxymethyl cellulose. Okay? And that, of course, is just a bead, except now its side chain is nothing more than our old friend acetate. Okay? Carboxymethyl, acetate. Nothing but acetate. Okay? Now, how do we actually get this to work? I'll show you an example. Here's a column where the beads are negatively charged. Is that anion exchange or cation exchange? Yeah, of course. This is a cation exchanger, right? Now remember we said proteins are going to have some positive groups and some negative groups. This protein has more negative charges than plus charges, so it's negative. So all this protein, all the red stuff's going to flow through. But the protein that has, in blue, that has more positive side chains than negative side chains, that's going to stick. Okay, and so this negatively charged protein flows through, but the blue one sticks. Okay, how do I get it off? How do I weaken that charge-charge interaction? Ionic strength, right? I can now take that same protein and I can do one of two things. So here's an example. Here are those three proteins. Here's a blue one, a purple one in the middle, and a red one. And you saw from before the red one flew right through, right? Because this had the wrong charge. But the blue one and the purple one, they're kind of stuck, and I want them to come off. So I change from a low salt buffer to a high salt buffer. That high salt concentration helps to shield the charges on that column. And that now allows the proteins to come off. Now, the one that has the fewest of the positive charges is going to come off the first. So this guy comes off first. That's the purple one. And then the other one comes off later. So even two positively charged proteins can separate on this column depending on the salt concentration that I use. Is there another trick that you can think of that I could use besides changing the salt concentration? What else could I change in my buffer? Right, perfect. I could change the pH. And then I could make my protein that was positively charged after initially negatively charged, and then it would come off. Fantastic.